Hello, hello, hello. Good. Hello, hello. Good. All right. Oh, you got your good afternoon, Alyssa. Good afternoon, Vivian. Well, all right, all right. Good afternoon, Stephanie. Good afternoon, Andrew. Good afternoon, Goof afternoon. Fast. Oh, sorry. Sorry. Good afternoon, Jayla. Hello and good afternoon, Wee She. Good afternoon to Mark and to everyone on behalf of Mark, CO Mark. Good afternoon, Jaylyn. Hello, Charlie. Good afternoon, Catherine with an I. Good afternoon, Lakshmi with a I. Good afternoon, Gabriella with a Yi. Hello, Michaela. Good afternoon, Catherine with a Y. Okay, awesome, awesome. I think that's right. And good afternoon, Jayla Video. Nice. Good afternoon. I appreciate it. Okay, I won't comment. But I appreciate it. Good afternoon, Wee She. Good afternoon, and video. And good afternoon, Andrew Video. Good afternoon, Gabriella Video. Good afternoon, Jaylyn Video. That's a good afternoon, Mark. Oh, and a lot of you are at John J. Clearly. Okay, anyway, whatever. I don't. It's like you show video, and then I'm going to sit there and comment on it. That's really helpful. Okay. So good afternoon, everyone. I think that's everyone. Did I say Vivian? Hello, Vivian. I think I said Vivian. And Alyssa. Oh, cool, cool. Okay. Okay, thank you. I appreciate polysaccharides. Okay. Okay. We're gonna get rolling. I still owe you a lot. Things are still very kind. I apologize. I'm just saying, I'm acknowledging. I know I owe you a lot. I'm just saying. And you don't, and I'm more behind than you. I am just saying. I'm gonna switch the, and I apologize. Things are still a little crazy. You are, I'm gonna switch the thing. Okay, and as at least one of you was sort of confirming, oh, sorry, that is not this class. Pardon me for a second. Yikes. Sorry. Okay. Just to confirm again, you should be in the lab tomorrow, physically. We should be seeing Professor Johnson tomorrow. I'm very excited about that. Professor Johnson is definitely on the, yes, which I totally appreciate the attitude and the patience and everything. I have total confidence in every aspect of the experience that you'll have with him. And once it starts, I will admit right now, there's a tiny bit of, there's definite certainty that he's the man that's coming. And there's definite certainty that I will not be there tomorrow for lab. Like I have to go to my other gig before I lose it. So I will miss you guys tomorrow. I will not see you. I will admit right now, just that there's like a 5% chance that something is going to snafu in the morning, something with, there's been a huge amount of paperwork that we had to get through with human resources and payroll and all those kind of administrative things to get him in place as fast as possible. So I'm going to admit, I don't want to like confuse anybody or create any anxiety, but there's a 5% chance that that paperwork did not go through in time. And so if anything goes wrong, and I can't, if something goes wrong, I will notify all of you, and hopefully not at the last minute. But if something goes wrong and we have to not have lab tomorrow, again, I'm not trying to raise false expectations, but just to warn you, there's a 5% chance that something bureaucratic or administrative is going to fall through. And in which case you would not, we just wouldn't do lab tomorrow. I can tell you that right now. There's no room for a different solution. Don't get your hopes up. Assume you're in lab tomorrow. I'm almost afraid to say this, but I like to, I'm more into open, transparent communication these days than the reverse, because so many things have been happening. So you come to lab tomorrow. You look forward to meeting Professor Johnson. He'll look forward to meeting you. But look out for a notification from me. There's like a 5% chance that something will go wrong. And or if somehow you get to the lab room and something seems wrong, like it seems locked or something, then I am telling you it's not your fault. And you don't have to look for an online thing or anything. If in the 5% chance something goes wrong, then we're just going to make up the work somehow later. Okay. Okay, I think I get that. I'm going to pretend I get that, even though I don't actually totally get the Eric Andrew part, but that's because I'm ignorant. Okay, but cool. Okay, cool. So let's get back to physics now for the brief time that we have together, or for the time that we have together. Yeah, I think I took a long time on 6, 7, 8 last class, last Wednesday, maybe too long on 6, 7, 8. So I think we are finally really ready. Finally, I apologize, or I assert, we're ready to do 9, question 9 of homework 1 now, the last question. And I do know, no, I don't know. Okay, so we're up to question 9. In a way, that's where this has all been leading. In a way, the labs that you have been having with me do ultimately figure into this question 9 large topic. Okay, so but here we go. So question 9, and obviously stop me once I get rolling here, stop me with any physics questions, but okay. So, and certainly stop me if I'm in the wrong place or whatever, but we're still on thing on the spring. We're on a math. More people are entering from the lands of polysaccharides. So the question, so we've been looking at this mass that's been going back and forth on the spring. It's been oscillating. I mean, I'm saying it's been going back and forth, and it's been going back and forth in a very patterned, regular, predictable, symmetric way, right? It's not just going back and forth like spastically or randomly. It's going back and forth in a very regular, periodic, patterned, predictable way, much like the objects that you looked at in the lab, both weeks, right? So ultimately, this kind of regular, patterned, steady, constant type of oscillation, we are ultimately going to call harmonic oscillation. I'm calling it that right now. Ultimately, what we're looking at here in both the labs that you did and in this question, all these questions, we're looking at harmonic oscillators. We're going to land at an even more precise definition of harmonic fairly soon. But for the moment, harmonic means an oscillator that is regular and patterned and constant in kind of all the qualitative and quantitative respects that we've mentioned so far. Okay, now question 9 asks a very seemingly simple, not anyway, it asks a very seemingly simple, and I would argue seemingly fair question. It's just asking, hello, good to see you, welcome back to the land of monosaccharides. Thank you. I do appreciate the hello, even though I'm acting like a spaz, because that's what I do. Okay, yeah, so the question is just, you name the time, or I name the time, can you name the position? I name the instant, can you name the position? I name the point in time, can you name the point in space? That's literally the essence of physics. Like all physics questions, in a way, come down to that. Where's this thing going to be at a certain moment in time? Nothing could be more standard physics. And also, in a way, almost nothing could be more simply expressed than given t, what is x? But notice, it took us all the way to question 9 to get this. It's certainly a simple question to express, and it's certainly a fair question to express. And it may even be the most obvious thing to want to know about this mass of the spring. Like, I'm going to say, if you really step back and think about it, it's almost shocking that we haven't even asked this question yet. We've been on the sheet on this system for like 4 weeks now. And we've asked all these questions, and not once did we ask the most like sort of almost obvious, and not obvious to answer, but obvious to ask physics question of where will it be when, right? Well, like, what have we been asking? We've been asking we've been asking essentially, we've been asking about relationships between where it will be and how fast it's going, or how fast it's going and where it will be, or even at what rate it's accelerating and where it will be. But we've never actually asked anything yet that treats time as the independent variable. okay? I'm going to say right now, and there's a reason, because it's actually trickier to know right off the top of our heads than we've been asking questions treating space as the independent variable. And that got us off on this whole like 2-week journey of reinvestigating work and energy theorems, because that's what work and energy are about. And work and energy conservation are something that we actually can say something about on the system. But we've never actually yet approached a straightforward kinematic question that treats time as the independent variable. So before I go any further, I'm going to say right here that there's nothing special about the moment one. Like if this question is going to get involved, it's not because I'm asking about t equals 1. There's nothing harder or easier about t equals 1. Really, I'm just ultimately trying to figure out, can I know a relationship between x and t at all? If I can figure out that relationship at all, then I'll plug in 1 for t and I'll spit back x. So I'm first just going to note what we really want. Oops, sorry. So I'm going to note first Now I'm going to note this for 2 reasons. So I'm saying I'm almost transforming the question, or I'm generalizing the question. I'm going to say all the math work that I'm going to do right now, or any work that I'm going to do right now, is going to be in the search for a function that maps t as the independent variable to x, the dependent variable. And notice that's what I've been sort of arguing is all of what you're ever trying to do in lab. Like it's not always x and t, but all you're trying to do in lab is discover or invent or create or establish functions, one variable as it depends on another. And I'm going to say now this is what we're doing in theory too. Like again, just to put in perspective, we might have once thought of science or physics as an area in which we use equations to answer questions. I'm saying really, as we get more advanced in science, it's really the other way around. The point of science is to develop equations, to develop general relationships between variables. And that's what we're being asked to do here, okay? Okay, just to tell you, like, to give you an example of what we're trying to do here and what's going on. And again, I sort of tried to warn you at the beginning of the class, like this class, it in a way gets very mathematical in a way, but by mathematical, but it gets mathematical in the way that math actually gets mathematical, i.e. we have fewer and fewer numbers in physics 204. We have more and more general relationships, things that look like mathematical expressions. But by mathematical, I mean with lots of letters in them, variables and constants, okay? So that's, we're looking here for a function. The really question on is asking, okay, given something that oscillates back and forth in this regular way, how does its position vary in relation to the time? Like, what is the general rule for how you know where it's going to be after any certain amount of time has passed? Like, that should be do we have that kind of description of the behavior? Do we have, in other words, a strict equation of motion for this oscillator? We have many equations so far. We've got equations, kinetic energy, potential energy, but truly, in the language of physics, an equation of motion tends to actually mean an equation that maps x to t, that or t to x, but x to t, an equation that takes time as its input and spits out position at its output. Like that's the real thing that physics is always trying to do for different systems. So an example of an equation of motion, an example of something that would have the kind of form that we're looking for would be down at the bottom, written in blue, but crossed out in red. What I wrote at the bottom, like I intentionally wrote it, but crossed it out because like I want you to know it's like the wrong answer here. But down at the bottom, written in blue, is x equals 1/2 at squared plus v naught t, good old kinematics equation. Now that is an equation of motion. That's the type of thing that we're looking for here. It maps x as the dependent variable to t, the independent variable, and has some other letters in it like a and v naught, but they are constants in that equation, right? So that, and we used to use that equation all the time in physics 203, and it's still like true and flying and sitting around in physics as a true statement, but it's true for certain conditions, good old conditions that used to be often true in physics 203. And that condition is constant acceleration. Like that equation of motion works whenever you have an A that you can plug in steadily for all T's, right? So it works for a lot of really important examples in physics, such as free fall near the surface of the Earth, where things fall at a constant rate of acceleration. So it's the right type of thing we're looking for. It's an equation of motion, but it doesn't meet the conditions of the harmonic oscillator. The harmonic oscillator is like a new set of conditions in physics. What is the condition? The condition is Hooke's law. So we're looking for an xt function that actually does not assume a is constant, that actually assumes Hooke's law. So I'm gonna, okay, so, but we'll know we're there if we find an x of t that meets the constraints of Hooke's law. So sorry. Okay, sorry. Okay, so just for those who are tracking along, like everything I'm saying right now is in the realm of like general definitions and principles for answering this question. So we're looking for again, I've sort of changed the WIQ. The WIQ, the what is the question, was at t equals 1, what's x? But I'm saying really as a physicist, the question really is, given t in general, what is x? In general, that's what I'm saying. The real question, so like we're solving for x as a function of t, and I'm saying the condition is, well, the specific condition is f equals negative kx, Hooke's law. And I'm also reminding myself that in general, what's certainly true, like always in classical physics, and what is I think applicable now is Newton's second law, F net equals ma. So those are my two like GDPs for this. Now I'm going to start doing some work to apply. So I'm going to say, okay, here, oops, sorry. Okay, I'm going to say then, okay, so in general, the net force acting on a system produces the acceleration of that system. There's only, and I'm looking horizontal, and there's only one force. I'm looking horizontally here. We're looking to find x as a function of t. So there's only one horizontal force acting on this object. There's only one force acting in the x-axis on this object, and that is the spring force So the spring force, it does constitute the net force on the system, right? So I can literally say, okay, like this is the knowledge I have of the spring. And again, if I were taking a test or an exam or something right now, like maybe I don't, like I'm looking for X as a function of T. It's actually a hard question. I might not know the answer right now. I might not even know how to get to the answer. But this is how I'm writing down everything I know first. I'm writing down truths and then I'm going to make them relevant. So here's a true statement right here. Now, I might for a moment not know where to go with this. Like that's certainly not the answer to the question. Why is it not the answer to the question? Because that relates X to A. And what I'm trying to do is relate X to T, right? So, I mean, of course, what might occur, what might enter my mind is, okay, so I don't want to get rid of that A and I want to relate it to T. You might say, right, I need an equation, a concept, a definition relating A to T so I can sub out, swap in. One might say to oneself, okay, I guess I remember from, you might start scrambling through, I don't know, a list of equations from physics 203 or a list in your brain. And something that might occur to you is, oh, yes, the definition of average acceleration, A bar, is change in velocity over time, V minus V naught over T. That might occur to you, and that's not a crazy thing to occur to you. And you might even write it down if it's keeping your brain wheels turning. But I'm not going to write it down. I'm going to caution myself because that's the definition of average acceleration. I'm not talking about average acceleration here, and I don't want average acceleration because I do know that the acceleration is changing all the time here. And I'm looking for very specific, I'm looking to relate a specific point in space to a specific point in time. I'm really trying to get down to the point level here in this question. So some sweeping average is not going to be like ultimately helpful for me here. Can I relate acceleration to specific moments in time? Well, yes. The instantaneous acceleration, the rate of acceleration at a moment of time is the instantaneous rate of change of velocity at that moment of time. That is, instantaneous acceleration is the derivative of instantaneous velocity with respect to time, which is the derivative with respect to time of position with respect to time. In other words, acceleration is the second derivative of position with respect to time, right? Like I'm saying, and how did I, well, I'm saying this. Right. And perhaps, honestly, perhaps maybe this recollection that I just made, perhaps this counts as a GDP. I mean, it does count as a GDP. This is the definition of A without a bar over it. A acceleration at an instant is the derivative of position with respect to time, right? I don't know if you think of this as a math concept or a physics concept, but literally it's a triple equal sign. I mean, you could say this, if it helped, I don't know. I'm saying it's the first derivative of velocity, and velocity is the first derivative of position. So acceleration is the second derivative of position with respect to time. Right? In other words, acceleration is a good old concept that relates position as the dependent variable to time as the independent variable. It is the kind of relation we really want here. And why did I even think of it? Because I'm trying to relate acceleration back to time because that's what I need. Like I don't walk around thinking this all the time necessarily, but it's totally the key that I need here to unlock this situation. So I'm going to go to the next page. So now I'm getting somewhere. Okay, now actually, if you look at what I have here, I have an equation now. I'm not done. I'm not done. But I have an equation now that treats x as the dependent variable and treats t as the independent variable. I know it's treating t as the independent variable because it's in the denominator of that derivative expression, right? Like it's the run, not the rise on some graph. So, and everything else, I don't know if I want to make that, well, I guess I do. Everything else in this equation, everything else is a constant, right? They might still be letters, but they are constants. So there are only two variables in this equation. One is dependent, the other is independent, and they are precisely the ones that I'm ultimately looking to relate that way. So this is very good. This is progress. This equation that I have here actually does contain all the information that I'm ultimately seeking to find, but it's containing it in a kind of strange package or an unusual package or a new package. And it's certainly not the final package that I'm looking for. I'm looking for x as a function of t, and it's giving me x as a function of the derivative of x with respect to t. Like, that's a little clunky. So I got to do something with this. I got to unpack it or somehow like start relating it. I got to start unpacking it or manipulating it to get it to where I want. First thing I'm going to do is I'm just going to rewrite it slightly. I'm just going to rearrange it slightly to make it into a form that is more common and clean for mathematicians and physicists. I'm going to isolate that derivative, because the derivative is like the intimidating part, perhaps. I mean, to all of us, the derivative is certainly the complicated part, and it's the part that I wasn't like looking for. I didn't want a derivative. I just want a function. So I'm going to isolate. So, and this is a thing in math and physics, like take the part that is bothersome and focus hard on it. Don't like avoid it, focus hard on it. So I'm going to rearrange this. I'm going to say so I actually did two. So I isolated the derivative. And then what I also did is I sort of gathered all the constants together and put them in a little package and kept the variable separate. So now what I have, we're not done. We are not done. But we have a kind of clean and actually sort of standard looking expression here. It relates a derivative to the dependent variable itself, right? This is not, so I'm going to write on the next page exactly as it is, okay? But so this is an equation. This is an equation. In fact, this is a function. And in fact, this function has all the information we want and maybe no other information. Well, it has all the information we want, but it's not in the form that we want. But it certainly is an equation and it certainly is a function. So let me break it down for a minute. Break it down. So I'm just rewriting it first. And you might guess this is the equation that I've sort of written on the front page of notes for the last 2 days. I mean, this is what we're trying to get at. This is certainly an important thing. Sorry. Sorry to keep changing. You can leave that word. The word that I keep changing, you can leave it. It's okay. I'm just being picky myself. But okay. Remember, well, okay, just to remind you again, what we're seeking, like always, ultimately, a simple function that we want as the answer to this question 9 is we want independent variable as input. We want dependent variable as output. We want dependent variable as a function of independent variable. Like that's like almost like the definition of a function, right? In this case, we want x as a function of t. What we have here is derivative as a function of dependent variable. Dependent, right? Like so there's a couple of unusual, possibly even confusing or maybe intimidating elements of this expression that we have here so far. Like here's like actually kind of 3 reasons that we're not done yet, that we don't have an answer. We don't have something that we can plug 1 in for t and it will spit out the proper x. There's kind of 3 reasons. Okay, the first one is the most minor. It might be intimidating, but the first reason is that this gives a second derivative rather than the first derivative. Now I want to acknowledge that if you're paying attention, if you're tracking this with me, the thing on the left-hand side happens to be a second derivative, not a first derivative. That can certainly make the whole thing more intimidating. It can actually often make it harder to solve. Like it has implications, but I actually want to tell you right now, don't let it distract you when as we pursue other aspects of this. The truth of the matter is the fact that it happens to be a second derivative, not a first derivative, is ultimately to us kind of a detail. So I'm saying it, but now I'm going to say a whole bunch of things that are just about the fact that it's a derivative of any kind. Okay, so the first point is it happens to be a second derivative. What's on the left-hand side? The second point is that it is a derivative, period. Like it's a derivative. It ain't the variable. It ain't x. It ain't t. Like if it were t as a function of x, then we would just like algebraically rearrange things and we would get x as a function of t and we would be happy. And like that's happened to us many times before in physics. This ain't that. On the left-hand side, what we have is a rate of change of x with respect to t, right? Like very specifically, honestly, a rate of change of a rate of change. But we are relating x to t here, the rate of change. It's like a slope of a slope, if you like, whatever. That's what's on the left-hand side. Neither x nor t, but a derivative. Then that's issue number 2. Okay, if you're tracking this, and please do maybe write this down. Like I'm saying, issue number 1 is it's a second derivative. That's annoying. Issue number 2, much more important, is it's a derivative at all. It's a derivative on the left. We don't want a derivative. We want the variable. We want the dependent variable isolated by itself on the left. Issue number 3, and here's a really important issue. Again, please maybe be writing these down. Issue number 3, when I say issue, I mean like reason we are not done, reason we don't have an answer yet, reason we have to pause. Issue number 3 is that what the derivative is being related to, or like expressed as a function of on the right-hand side, is the dependent variable. Okay, that is huge. That's so huge. I'm going to remind you right now. Oh yeah, and I guess that's what I've written here in words, but I'll leave it. Okay. Okay, very important point. Which I might make a separate video just on this alone, honestly, or because sometimes this takes the thing I'm about to say sometimes takes people practice. In a way, I guess we practice. Anyway, what I'm saying is this. We're trying to get x as a function of t. We did a little physics, a little math, and suddenly what we have is derivative of x of, sorry, what we have here is derivative of x with respect to t as a function of x. That's annoying. It's not what we want. We have to now do something. But you might be thinking, well, okay, we have to do something, but I don't think it's not that big of a deal, Yavrobam. I mean, don't come on, it's not that big of a deal. You might be thinking, for example, well, we want the function, but we have the derivative, or we have the derivative of the derivative. So you might be thinking, and by the way, so you might be very intelligently thinking, well, we want the function, but unfortunately what we have is the derivative. So didn't Yavrobam make a big deal last week, and didn't my math teachers make a big deal for like semesters upon semesters, didn't they all make a big deal of the fundamental theorem of calculus? Didn't they all? And if you're thinking anything like this, you're not crazy. You're very, very smart to be thinking this up. So let me address it. You might be thinking, well, if you want the function, but you have the derivative, just freaking invert that derivative, just unwind it, just do it backwards, just do the antiderivative, just use the fundamental theorem of calculus and realize that there's something called an integral, which is the derivative backwards. So just do that. And then you might even say, I understand it's a second derivative, Yavrobam. Don't get your knickers in a twist, whatever that means. Just like do the fundamental theorem of calculus twice or something. You might, and if you're even remotely, even vaguely, even if integration even passed through your mind at all, once I wrote this or once I wrote the problem, then you're a very good person and a very good student. And I heap praise upon ye. And I'm not even upon you. I mean, not just, I mean, you. I'm saying if you're thinking at all, like, I guess we have to do some kind of integration here or something, you are very wise to think that. And hopefully, if you're not thinking that at all, you now hear why I'm saying, no problem. Hold on. There's a direct chat about handwriting. Hold on a second. Okay, so let me read the bottom. Yeah. The two words, but I'll read the whole thing out loud, but the two words are merely use. So let me read this out loud. Really good point. So someone's asking in the direct chat about handwriting. I'm sorry, I'm getting my knickers in a twist, and I don't even know what that means. And it's probably gross. What this whole thing says, in blue, it says, the above equation expresses a second derivative as a function of a dependent variable. And then it says in parentheses, we seek dependent variable as a function of independent variable. Like that's what we want, folks. We want x as a function of t. In the lab, like last week, you wanted like capital T as a function of like theta or something. Like we always want output as a function of input. That is our goal as physicists. In this case, we want x to be the output as a function of t, the input. Now here, well, we don't have that. Here we have derivative as we have rate of change of variable as a function of variable. Like that's what we have here. Now, but you might be saying, well, that's not that big of a problem. That's happened before. Like that's why I learned. You might be thinking something very, very intelligent. Like, really, is this that big of a deal? And I don't mean to say it's that big of a hard deal, but it is kind of a big deal. What you might be, so what I wrote then in parentheses in the black at the bottom of the page, I wrote if IFF, if and only if, that is, if and only if the variable on the right side were independent, if i.e. t. If we had this expression at the top, like d2x dt squared equals negative k over m t, oh, then what it says here, and the person's asking about my handwriting, then we need merely use FTC, fundamental theorem of calculus, and integrate, admittedly, twice. Like, let me make this really clear. Like, to be honest, often in classes now, I will stop and we will do a bunch of exercises practicing the exact thing I'm saying here just to see, oh, cool, thank you. No, awesome, thank you. That was very helpful, honestly. And by the way, put that in direct chat person who asked me about handwriting and to whom I'm addressing right now. Please put it in one of those participation Hooke things for points. But anyway, to everybody, often I would stop right now and ask people to practice the very thing I'm saying. I don't actually think that would be productive right now. So just please hear me out. I'm saying that big expression on the top of the page, that big expression on the top of the page that we have to unpack somehow. The reason we have to unpack it with some degree of care and thought is 100% because the X on the right-hand side of the expression is not a T. If it were a T, i.e. if it were the independent variable, i.e. if it were the letter that's in the denominator of the thing on the left-hand side, then what we'd be saying is, oh, we don't have X as a function of T, but we've got rate of change of X as a function of T being related to T. We would be saying, oh, we don't have X as a function of T, but we got the derivative of X as a function of T. And hey, we all know that the derivative backwards can be done. Like we can anti-differentiate, and we call that often integration. So if we look at for X, but we have dx dt as a function of T, I don't know why we'd be talking in this voice, but like we would be just to get attention. We would say, oh, no problem. Let's undo that dx dt. Let's anti-differentiate it. Let's like do an integral or something. And then we'll have X as a function of T. If you're thinking anything like that, like why don't we just freaking integrate and move on with our lives? Or especially if you're thinking, why don't we integrate twice because it's a second derivative and move on with our lives? You're very, very smart and very much paying attention to think that. But I'm here to say it's not that easy, unfortunately. And it's why we have to be careful about what the fundamental theorem of calculus really means last week. This is not telling us rate of change of X with respect to T as a function of T. Wait, I'm going to read that in a second. But this is telling us rate of change of X as a function of T, like with respect to T as a function of X. In other words, what it's saying, but first I'm going to read the chat because I have a feeling it's going to be something. I think I get that because of the voice. Yeah. Oh, that's wow. That's like, I'm almost offended, I think, but no more so than how offended I am by the voice that I just used. Okay. So, but I'm also going to take that joke and I'm going to take like the handwriting request as sort of testimony that people are totally paying. Clearly, at least two people are paying attention, and I appreciate that. I'm sure many more, but I appreciate that two people are paying attention. And what I'm saying ultimately is this. Oh, wait, wait. Ha! Ha! Oh my God. Okay. I just got something in the direct chat that totally, okay, there's at least 3 people paying attention. And the person who just made that clear in the direct chat totally should submit it for participation, as should the other 2. And I'm like, that's never happened before. Just for whatever it's worth, someone in the direct chat just literally wrote the number 3. And I didn't get it at first. In fact, at first I thought it was some new like emoticon-y kind of thing that I don't get. Like, you know, 3 with a caret means like word to the mother or whatever these things. Like at first I was like, oh God, I'm so out of touch. I don't even know what that. And then I realized that that person, he or she was saying, no, there's at least 3 people paying attention quietly. You jerk, Yaverbaum, you didn't write that. But anyway, that's hilarious. And I totally appreciate it. And I should start to, wait, how do you, Oh my God. Wait, but now, all right, things are getting crazy in the direct chat. It's getting out of control. I can see why it's direct and it's making my voice go in the other direction. Welcome to my bar mitzvah. Okay, things are getting, everybody who's in the direct chat totally should submit for participation. It's great. I love it. I'm going to keep going because the math is hard. But yes, I love you guys dearly. I should like do lab with you someday or something. What? I did not say that. Okay. I'm saying this. And I will look at the second, bear with me for a second. Okay, now this, I'm going to look in the chat for a second. And again, no matter how far we do or do not get with this today, this is an important, this is everything I'm saying right now. I don't know how anybody's reacting, and I will look in the chat in a second. I just want to make it clear because I know I can go off on tangents, or I can end up sort of preaching sermons that were not requested. This is not a tangent. This is not off the topic. This is the topic that I'm on right now. And to be totally honest, if this ended up taking me the rest of the semester to unpack with you, I would consider it worth it. Okay. And it's a mathy thing. I want to say now, oh, that's funny. Wait. Okay, wait. I'm definitely gonna have to look in the chat in a second. Hold on. I think I'm back. But let me just say this, and I'll pause. I'll look at the chat, and then because this is like near and dear to my heart, part of this course. Okay. And I have to be clear about it, or I try to be clear about it. What we just stumbled on, what we're stumbling on now that we're trying to solve, like, please remember again, we are trying to get x as a function of t. That's really what we're trying to get in question 9, x as a function of t. Ultimately, so that we can plug in the number 1 for t and see what it spits out as x. But really, there's nothing special about the first second. We're trying to relate position to time for a harmonic oscillator. Let me say that again. Our goal here is to derive the equation of motion for a harmonic oscillator. And by the way, right here, we're trying to do it in theory. It's something that, as you're beginning to experience in the lab, it's something that a lab could be used for. And ideally in physics, both would happen. There'd be a theoretical analysis that would have certain advantages and disadvantages. Advantages being that it would be exact and perfect and like without error. Disadvantage being that it would be abstract and sort of disconnected from anybody's reality. And then there'd be stuff in the lab that would be totally connected to people's reality, but would be imperfect and have errors. And ideally both, and that is kind of what we're doing here. Ideally, both threads would be occurring and then meet up and communicate to attempt to get an equation of motion for specific physical conditions or constraints. Let me say again, in a way, this is the only and always job of any physicist. The only thing that makes one area of physics different from another or harder than another, whatever, is that the specific conditions or constraints of a particular physics situation might be very, very complex or sophisticated or modern. They might be like involving the atom or something like that. But all physics is, in a way, you specify a bunch of conditions, and I will try to get the equation of motion for the given system under those conditions. That is what we are trying to do right now in question 9. In our work, in our attempt to do that, what we've stumbled on, what we've just sort of uncovered from a couple of steps of algebra is this equation in brown at the top of the page, which from here on in, I'm going to call a differential equation, because like it is one. This is a differential equation. I want to say a number of things about that. That's a very, very big area of mathematics and physics, is discovering and solving differential equations. And again, I know there's things in the chat I will look in a second, but let me make our goal here now then. What we thought we were just trying to get the equation of motion for like a system. Now our goal has just become, our goal now is to solve this differential equation. When I say solve it, I mean get another equation out of it, right? To solve it means somehow unpack it so that we, rather than having a derivative being related to a particular variable, we get a dependent variable related to an independent variable. We have to solve this differential equation. That now becomes our goal. Again, I know I'm screaming and I know I'm not looking in the chat. I don't know why I'm screaming. Well, because I'm excited, but I'm also like nervous. I'm nervous because I want to make clear before anybody starts like phasing over. Like, I think solving differential equations is very exciting. I also think it's very central to physics. I think it's actually what really goes on a lot of the time in higher level physics or in PChem, for example, or something like that. However, I also know it's a calculus thing. And I know that if you're anything like I was in certain classes, you might be thinking right now, whoa, 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 you just did like some derivatives the other day, and then you like acknowledge that I might be kind of fuzzy on integrals, and then, but you gave me some integral stuff, but now suddenly you're talking about differential equations. Like, well, at least I was required to take the other math classes. You might be thinking, wait a minute, I never took a class in differential equations. We never learned how to solve differential equations in my math class. That is true. I want to rush to say, absolutely, absolutely. And that's a good thing. Wait. Okay, wait, all right, fair enough. But wait, I want to say, I'm about to get into differential equations with you guys, which I do at this point in the semester, every single semester. It's not because I think you've already had them. Not at all. I think you haven't had them. I think we're stumbling on one as physicists and we need to solve it. Just like the original physicists, whether it was Hooke or Newton, stumbled on this relation, whether they called it differential equations or not, they had to solve it for physics purposes. They developed some math that made sense. They didn't look it up. They didn't have it handed to them, whatever. They developed some thoughts that made sense, and then later, like, landed in math textbooks or whatever we called math. I've said to everybody before that sometimes I understand why sometimes we have certain courses required in math in order to do the physics, but often I'm of the real experience and opinion that often, like, it could go easily the other way around, that we don't really understand the math until we have a physics context for doing it. I know for a fact, I didn't understand any of this math stuff until I was doing it in physics. And I know that sometimes when we get these things in a math class, sometimes it's even all like a little bit of a turnoff or an intimidate, or makes us think we don't understand things because it goes too fast or whatever, that then turn us off to those things. I'm here to say, just like, yes, I assumed you had integrals in classes, but maybe had some negative feelings or unresolved feelings about them that I had to work against in order to give you integrals in this class. I'm now saying this is a different situation. This is fresh start. I want to show you something about differential equations. I do not assume that you've seen them before at all. I, in fact, happily assume that you've not seen them. And we're starting from like a tabula rasa, a blank slate. And I will look in the chat. Let me say, we're going to try to solve this differential equation. I'm going to show you how, obviously. And I'm never going to expect you to solve a differential equation in this class that we don't like do together. We're going to solve a couple of differential equations as physicists, the same way that physicists do, and in the same order that physicists have had to in order to do their physics. For example, I'm going to say, I mean, we're not going to solve all the differential equations in the world. You're not going to be tested on 1,000 different techniques. You're just going to know the differential equations that we need to know for physics, just like physicists did. Okay. I will look in the chat in a second, but one of the reasons that differential equations come up in physics, like this one came up, because this is just really an algebraic way of rewriting Hooke's law, combined with Newton's second law of motion. This differential equation here really is just a mathematical way of writing a physical expression we already had called Hooke's law. What makes it, and I really will go to the chat. Actually, okay, wait, I'll pause for a second. I'll go to the chat. But so we're going to solve this thing. We're going to solve it in a physics way. I'm going to show you, or I should even say, well, I'm going to show you the solution to it in a physics way. And when I say physics way, one thing I mean about that is you'll notice this is technically called a second order differential equation. It's technically called second order because it's relating a second derivative on the left-hand side to the dependent variable on the right-hand side. So technically it's second order. So if this were a math class, entitled Differential Equations, how to solve them, and there are certainly such math classes, we would start with first order, because the whole point of the class would be to learn a million differential equations and learn different techniques for solving different ones. That's not our context here. Our context here is to do physics. So we just stumbled on a differential equation. The first one we're stumbling on happens to be second order. And that happened to Newton and it happened to Hooke. So it happens to us and we're going to solve it. We're not going to invent the whole alphabet of differential equations. We're just going to try to unpack this one and deal. And that's what we're going to do in a second. I'm going to look, but they're really excited. They are. If you don't, all of my speech right now is defensive as usual for some reason. But that's because I feel defensive. Because honestly, I was very freaked out when I first had to deal with calculus. And I was freaked out when I had to deal with differential equations. I was. And I was particularly freaked out when all of a sudden I was expected to know it from one context and then apply it to another. I really was. I'm here to tell you, you don't have to cross apply anything from any other context and try to come in here with an open mind. I'm going to show you something that I think is cool called the differential equation. And I'm going to show you a solution to it. I'm first going to look in the chat, but then I'm going to tell you before I go any further why differential equations actually are sort of exciting and cool and kind of a thing unto themselves. Let me look in the chat. Oh, okay. Okay. Oh, huh. Whoa. Okay, wait, these are funny. I think okay, the stuff in the chat is funny, acknowledged. It is funny. In fact, it's so funny that some of it I don't get, but most of it I think I do. I think I do. Wait, I'm just wait, an S. Oh, wait. Actually, one of these might not. Tell me in private or public. I think this stuff is funny that's in the chat and it's cool. And believe me, I like the fact that people are alive, but I'm almost thinking that one little tiny piece of it might be serious. So tell me in private or in public, when it says SN2 reaction, does that mean you have seen, is that a serious thing that you have seen? Or is that just because I said PChem? I guess, oh, it's all a joke. Okay, fine. Okay, and appreciate it. So, and as you all look, talk about, obviously anyway, okay. But I hope it's clear to everybody, even though I get spazzy like this and I fall off I still think it's worth it to everybody to have these joke interludes and have I really do. Even if it spazzes me out for a second, I would rather this be spazzy interaction between me and you guys and keep it somewhat light than not. Please know, even when I get all distracted, I still think it's worth it. and I hope you do too. But okay, look at what it says. One thing I'm trying to really say now, something that really escaped, that confused me when I was at a certain stage of undergrad, is the term differential equation. It doesn't just mean any equation that has a derivative in it. I thought that's what it meant. I thought, oh, differential equation, equations that have derivatives in them. So I totally thought like, well, haven't I been doing that every time don't I do that all the time in calculus? Like, what is this big deal about differential equations? Like, aren't we doing it all the time? Like whenever we take derivatives. And so therefore I didn't really know how to pay attention or like what I was supposed to be watching for when people said differential equation. What I'm here to tell you is really, I mean, yes, any equation that has a derivative in it, I suppose, is like at some really larger general sense, I guess technically is a differential equation, but not in the meaningful sense, not in the sense that people make a big deal of. What we're making up when we call something a differential equation, we're specifically saying this thing that's happening here, where derivative is being related to or expressed as a function of the dependent variable, not the independent variable. And let me remind, and that's a very big difference. And honestly, I didn't care about that difference, dependent versus independent, until it started making a big difference in like calculus and physics. Okay, like you learn about it in 7th grade, but and I think Mark had a cool way of remembering. Independent means I said it or something like that. He said, which is cool. Like whatever you have to do in your mind to get the two straight, please do, because it does make a difference, particularly here. If you say, and how you know, it's not like there's, oh, I change equals independent. That's awesome. Thank you, Mark. That's totally awesome. And by the way, that's person number 4 or 5 who's paying attention. Not that I'm counting, but he should totally put that. Mark, you should put that in one of the participation portal things. Not that any of you people need to boost your grade, but I'm just saying. If a derivative is expressed, I'm sorry, I'm saying this. Whoa, all right. I'm saying that this derivative is expressed as a function of the dependent variable, not because x is always the dependent variable, and not because t is always the independent variable, like it isn't. In fact, it wasn't in the lab you just did last week. I'm saying I know that in this context, t is the independent variable simply because it's written in the denominator of that derivative expression. Like that means it's like the run. So it's this axis of any graph. This expression is relating a rate of change to a dependent. Now that is what I'm ultimately saying here at the bottom of the page. I'm saying that if you really stand back and look at it, like even before you know the answer or whatever, that is some kind of feedback. If the rate of change of, so it's feedback. It's an interesting phenomenon. It's actually fascinating that we should be able to say anything about any differential equation. What I mean is this. Think of, like, I like Mark's thing, like the independent variable, something I choose or I set, right? I choose, I think he said. And another way you could loosely sometimes think about it is like independent variables is like cause, and dependent variable is like effect, right? Like, or you could think of it as input and output, but look, for the moment, loosely think of it as cause and effect. So an equation like this thing at the top of the page is saying that the rate at which effect changes in relation to cause depends not on the cause, but on the effect itself. That's weird. That's like an example of that. One of many examples of where a differential equation, like, well, no, the example in this case, like in English, what's happening here? We're saying, I want to know, like you name the time, I want to know the position. So you say, oh, no problem. Like I know how to do physics. You want the position? You want the position? Okay, all you need is like to know the acceleration. Like just tell me the acceleration at various times, and I'll use my kinematics equations and blah blah blah. And as long as you give me an expression for acceleration, and I'll be able to use the acceleration expression to tell you the position. And then you say, oh yeah, no problem. Okay, the acceleration, it depends on position. Like that's what's going on here. It's like cause leads to effect, but effect becomes the cause and leads back to effect. Position depends on acceleration, but acceleration doesn't depend straight on time. It depends on position. Like what? Like that's what we're saying here. That is why this is an interesting type of equation that even if I finish today and haven't solved it for you, and I apologize, but thank God we have Wednesday, it's worth like pausing and noting like why this thing is and why you might have gotten stuck at this point in the homework. And that's also totally fine. But why I want you to have thought about it. Like what's weird is we're relating a rate of change of effect with respect to cause to effect, not cause. Let me give you another quick example. It's like when you walk into the bank, where it's like I walk into the bank and I'm like, hey, how much money do I have in my interest-bearing savings account? And I'll try to write, well, I'm a professor. So they're like 0. And I'm like, okay, then I'm going to rob. No, so I'm like, how much? Do you know, I literally had a camp counselor once whose name was Rob Steele. Like his name was Robert Steele, Rob Steele. And I was like, that's a really weird name. But anyway, so if I walk into the bank and I say, right, I mean, apparently, oh, that's 6 people paying attention. See what she did? That's the other good thing about the, thank you, Jay. Yeah, apparently, I'm not promoting, wait, I think I was with that voice 20 minutes ago, but no, I'm not promoting robbery. I'm not at all. I'm promoting high interest rate lending. But no, say I walk into a bank and I'm like, hey, how much money do I have? Right. I'm like, how much money do I have in the bank? And they're like, oh, Professor Yaverbaum, you're a professor, so you have 0. No, they're like, oh, how much money do you have in the bank? No problem, we'll find out, but we'll check. But, it totally depends on how much interest was added to your account, like last night. Like how much you have totally depends on how much interest was added, because you have an interest-bearing account. So I'm like, oh, that's great. That makes sense. Okay, how much interest was added last night? And then they're like, okay, right. So I'm like, how much money do I have? And they're like, depends on how much interest we added to it, which is true, by the way. I'm not like, that would be true, right? And then I go, okay, how much interest was added to it? And you know where this is going, hopefully, whether you're following the jokes or the serious part. I say, how much is in the account? They say, it depends on how much interest was added. And I say, how much interest was added? And they say, depends how much was in the account, right? Like that's actually how interest works. And if you really just stop and think about it, that's weird. Like, I'm not saying it's not solvable. Apparently it is solvable because like banks work, but that's like a really weird idea. The rate of change, the amount that you change the account by somehow depends on, not on time, but on the amount that's in the account. It doesn't depend on cause. It doesn't depend on independent variable. It depends on effect, on dependent variable. To express what happens in computing the interest on an interest-bearing account, one actually ultimately needs a differential equation. The rate of change of money with respect to time depends not on time, but on money. That's what's happening here. The rate of change of position with respect to time does not depend on time. It depends on position. That is called a differential equation. When that happens, when the derivative depends on the dependent variable. Okay, that's the key, is that it's an X on the right-hand side, not a T. Again, even if I don't solve in the next 4 minutes, I do apologize, but that's not like, just to even understand the nature of the question, to me, like would have saved me months of psychological confusion if I had understood that the nature of a differential equation is not just an equation with a derivative in it. It's an equation that relates the derivative to the dependent variable. And it requires tools or thought. I'm going to say this now too, since I do know I only have 5 minutes. There is not just like one way to solve all differential equations. It's not like there's just rules like with differentiation. It's more like integration, where it's like a puzzle to have pieces moved around and have toolkit to apply to and have techniques. Some differential equations can be solved. Most cannot at all. How do we know in advance whether it's solvable or not? We don't always. It's like an experience thing, which is why there are whole classes devoted to it. We're not going to do a million of them here. I just want to alert your attention to the seriousness and sort of the intrigue of any time a physicist like slams into a differential equation. If they can solve it at all, it's very exciting because it means they have unbroken a sort of weird cause-effect chain that seems to be looping on itself. Ultimately, differential equations describe what we call feedback, something that feeds back on itself, like you put the microphone near the speaker, so the sound comes out of the speaker into the microphone, but then back out the speaker again, and you go, right? And that's what all phenomena described by differential equations have, that quality. Okay. Now, clearly I didn't solve it yet. I have 3 minutes. I'm going to write down a possible solution to it. And we're going to leave it at the possible solution, even though it's correct. But I'm going to look in the chat for a second. I think it's mostly jokes. So I'm just going to look. Yeah. Huh. That's really sweet. Direct chat person. No, I appreciate, even if that's a 10%, even if that's a 95% joke, I totally appreciate it. Okay. But so here's what I'm going to do with the 2 minute, and particularly since I didn't finish solving this, I'm going to write. So I'm admitting right now, differential equations are like a thing. There's not an algorithm for them. In fact, one way to solve differential equations, especially second order, I will write this down now. One classic method. And I know we have like a minute and a half. This will be the last page. What I'm going to, tell you right now, one method, even for mathematicians, for solving new differential equations, is they come up with a conjecture and then they verify. Like, they don't just believe their conjecture, but they test it. And if it passes a test, which you'll see, then it's right. That's called guess and check. But guess and check would not be math or science if it weren't for the check part, right? And the guess part comes from experience. But for us as scientists, as physicists, the guess part actually comes from lab experience. And I'll get straight to it. There's one. Okay, I have a minute and a half left. If I picture the situation of a mass going back and forth on a spring, if I picture taking lab data, for which you've done enough now that you could picture, but you didn't do specifically this. If I put time on the x-axis and I put position on the y, right? So I let a mass go back and forth and back and forth, and at each second asked where it was and where it was. To cut to the chase, what I think that lab data would look like, it wouldn't look perfect, of course, but I think the positions would be, they would start somewhere above zero. If I held the thing out away from equilibrium position and I let it go, it would come towards zero, go past zero, then it would turn around, come back to zero and go back, right? It would go back and forth and back and forth. But on the graph paper, it would go back and forth and back and forth. And it would do so smoothly, somewhat smoothly, not perfectly, but smoothly. And so it would look somewhat, I think, like this, right? I believe if I did in the lab, it wouldn't look perfect, but it would look somewhat like a cosine curve, right? So I'm going to guess that the answer, and we'll pick up on this on Wednesday, I'm guessing, this doesn't prove anything. I'm going to have to prove that my guess is right, but I'm guessing that x as a function of t, because I'm a scientist, from picturing the lab data, I'm guessing that it's going to be some sort of cosine of t function. But now, last thing with the 30 seconds left, I put a dash before the t and a dash before the cosine because I'm a scientist and I care about units of measurement. I don't think you can take the cosine of a second of time. You can only take the cosine of a radian or a degree of angular measurement. And I think that when you take the cosine of something, it spits out a unitless thing. Like it spits out 0 or 1 or 1/2 or radical 3/2. It doesn't spit out meters. So I'm going to need something to do to this cosine function to adjust the units accordingly. So I'm putting a dash before the t to adjust those units, and I'm putting a dash before the cosine to adjust those units. What kind of thing will adjust units? Constants. Remember, we said we have two goals: to get the shape and to get the details of a shape. Like whether we're in lab or in theory, the details of a shape are the constants. So we're going to leave it here. But I'm saying my conjecture, and I wouldn't lead you down a fault, like it will turn out to be correct. The conjecture. Okay, yes, yeah, absolutely, absolutely. Okay, so everybody has to go, but that's where we're going to put the conjecture to my answer to this differential equation to question 9 is x equals something, some constant times cosine times something times t. We'll leave it at that for now. We'll pick up Wednesday. Have a great day, everybody. Thank you for your total patience. Yes, have a great day. Thank you. Yes, no, you all have to, yes, thank you, guys. Okay.